Today you will be discussing the number system, operations on a different number system, and some codes that will be useful in the course of our study of computer engineering. The most relevant system that in use is the binary system. You see it here on the right. This is the system that the computer understands. On the other side here you see the equivalent decimal. So the first one is the 0, and here is the equivalent 1 and 1, 2, 3, and so on. We will study in this lecture how we do conversion between these two systems, the binary and the decimal, and some other systems as well. But first, we need to clarify some concepts that will be useful to us to understand this conversion operation. The first one is, what is the base? What is the expansion, right? For both binary and other system like the octal, hexadecimal. And we will be looking at some ways, some algorithm that help us do the conversion back and forth between the different systems. Let's start by describing what is a base. What we mean by base. A base simply indication of the number of a digit in a system. Let's consider first the decimal system. The decimal that we use, that we are familiar with, which starts from 0, 1, 2, 3, 4, 5, 6, 7, 8, up to 9. So this one is a decimal. A decimal, I mean 10. So we have 10 digits. All these are the digits that are part of the decimal system. So for the decimal, then the base will be 10. Okay, so the base is 10. Along with that is something called the power of any number, which simply indicates the if we take this base and multiply it by itself. So for example, if I take the base 10, if I multiply it by itself one more time, I'm going to use the dot here to indicate multiplication. 10 times 10. So instead of writing 100, we normally do, I'm going to write it this way. I see 10, and then how many times this base is repeated. So it is repeating one time, two times. So we say the power is 2. Similarly, if I have the base and multiply it 3 times by itself, then we just write it 10 to how many times? 1, 2, 3. In general, if I have a base, say 10, and I multiply it n times, let's say n repetition, then we say this is just 10 to the n. This is for the base 10. We can do the same thing for the base 2, which is the binary. With the binary, how many digits we have? We have just 2. We have 0 and 1. So in this case, the base is 2. Okay, So when I repeat that, so I multiply 2 times 2, then I get 4, which is equivalent to 2. How many times? 2 multiplied by itself 2 times. 2. If I do one more time, then I have 2 to the 3 or 8. Okay, and so on. As you can guess, this is 2 to the 4, or just equal to 16. So in general, if I have 2 and I multiply it by 2 n times, then this is equivalent to saying 2 to the power n. Okay, this is what is meant here in this part. Then the question is what happened if we have something 2 to the 0? So we know what it means, 2 to the 1 to the 2, 2 to the 0, or equivalently here, if I'm talking about the decimal, then what we mean by 10 to the 0. In general, if I have any base whatsoever, 10, 100, 1000, we don't care, anything, I'm gonna just indicate it as b to 0 is always equal to 1. So in this case, 10 to the 0 is 1, 2 to the 0 is 1. Okay, and you see it here. Then what happens if I have negative? What if I have 2 to the negative 1? This is the same thing to say 1 over 2. And 2 to the negative 2 is the same as saying 1 over 2 to the 2, which is 1 over 4, and so on, and so on, and so forth. Let's do one more time. 2 to the negative 3 is equivalent to 1 over 2 to the 3. So basically what we are doing, we get the number, we put it in the denominator position without the negative. So in general, if I have some base b to some power, let's say a, negative, this is the same as, so what I'm gonna do, I'm gonna just write 1 and copy the number here, b to the a without the sign. And this is what we mean by when you look at this side. Now that we know what does it mean when we say a base, what does it mean when we say power, we will see how using that knowledge we can express numbers that we normally use. For example, the number 967, we can write it to mean the same thing by using the base, as you can see it here. Let me elaborate here. So we have here 965, and we recall from school that our teacher telling us when we start from the right, from here the digit 5, this number, or this to be exact, this digit is in a position that is different from the 6, and the 9 is different from both. So the 5 occupy the ones position, the 6 occupies the tens, and finally the 9 occupies the hundreds position. So what that mean in numbers? In terms of number, this means this. we take the first one, 5, and to say that is in the ones, then we say that is multiplied by 10 to the 0. And we take the 6, we say plus 6 times 10, and because it's in the tens, we raise it to the power 1. And finally, we take 9 and multiply it by 10, we raise it to the power 2. As you can see, it's very simple. We write the numbers from right to left. We just multiply them by the base, right? And then we add. Okay. How we start adding? Start from 0, 1, 2. Now, if we add these, what we will get? We know that 10 to the 0 is just 1. The addition is just 5 times 1 is just 5. And here, 6 times 10 to the 1, 10. This is just 60. And finally, 10 to the 2 means 100 times 9, that is 900. So, as you can see, it's 965. And we can do this for any base. Here we use just the base 10, but we will see later we can use base 2, base 8, base 16. These are the systems that are relevant in computer engineering and in computer science, but this method works with any system. So, writing a number such as 965 in the form of polynomial, you can see it is polynomial, is called expansion, and this idea will be helpful to us when we do conversion between different number systems. So assume that we have the number 101 and somebody told us this is not decimal, this is binary, and people normally indicate that by adding a subscript here to indicate this is binary and not decimal. So we're going to use the same idea as we did in this example. All right, let's do it. So we're going to start by writing the digit. The first digit is 1. And then we're going to multiply it by the base. And the base here is 2 because it is binary. All right. And since this one is in the position of the ones, we're going to put 0 as power. And we say add. And we take the second digit and we multiply it again by the base, this time to the power 1, and finally we get the 1 and we multiply it by 2 to the power 2, and then we do our calculation. Let's do that. So we have here 2 to the 2 is just 4 because 2 times 2 is 4, and this one we just cancel it out because it is multiplied by 0, so it is 0. And for this one we have 2 to the 0, which means 1. 1 times 1 is 1. So what we are left with is 4 plus 1, which is 5. Therefore 101 in binary is equal to or equivalent to 5 in decimal. So this is base 2, this is base 10. Let's look at a more complicated number. In this case, we have this lengthy number. We see it in front of us here, but we're going to be using the same method. All right, so here I have it written. So the same as before. We take the first one, first digit, we put it here, the first, the second. So we have this is the first, this is the second, and so on. And this one is the final one. So we call this one the most significant bit. This is the most, the leftmost bit. And as you can see here, the power is being increased, incrementally increased from 0, 1, 2, up to the last one. All right, and then we just simply calculate, and we get 351. Another example, so we have this number, and typically when we read decimal number, we read them from the left. So we say 1, 1, 0, 1, 1. So we're gonna convert this one into decimal, the same style. Okay, the same style. This is another way. You know, sometimes students, when they learn the basic or the essential method, then we try to make things easy for ourselves. So one way to do this is to start by writing down the digits. We start from power 2 to the 0, to the 0 is 1, 2 to the 1, and then, or just simply start from 1, then multiply it by 2, they give you 2, and multiply 2 by 2, you get 4, and 4 multiplied by 2, you get 8, and 8 multiplied by 2, 16, and so on. You keep doing this, and this one, 4,102, 8,208. And we do that. So if somebody then asks us to find out the value for this, we just try and go and find the location of this digit in the table. So we have it this way. Why is that? Let's have a look here. So we have this number. So we just write the number. Okay, you're starting from the right. So this is this guy is here, and this is the 0. This is the 1 here, and this is the final one here. And we write zeros. We know there are zeros always to the left, but it's not important. Okay, you don't have to write them. You don't have to, but it's good to know that there are always 0 to the left of any number. And there we go. We indicated the location. And then finally what we do, we just write down the values underneath. You just copy the value here, right? If there is a 1, I just write the number, okay? Like I did here, 8, 8. And here I write 0 because I have 0 here. I don't have to write 2. And finally I have 1. And then just there, I add them up to get the final result, which is 13, because 8 plus 4 is 12, and 1, 13. So I hope this method is easier, but it's still based on the expansion that we mentioned in the beginning. Let's move on to octal. Octal means 8 in Latin. So the base octal is 8. This means that we have 8 digits from 0 to 7. If somebody asks us to find the equivalent of some octal number, so we have here this number, 7016. This is an octal, and we know this by noticing that there is a subscript indicating the system. So this is octal. All right. So as you may guess, the base in this case will be the base 8. Same story here. We take the first digit, okay, and we write also the base, and because start in this is the ones, so we put 0. We take the second, right, and we write the base. We increment it by 1 to give us 8 to the 1, and we get the 0, and the base incremented by 1 to give us 2, and finally the 7 here. So the 7 is the most significant digit, to write it here, and because the base already, the one before is 2, so it'd be 3. So in short, what we have, we just write the numbers, okay, 6 1 0 7, and then we write the base, right? We're starting from 0 1 2 3, and then we just evaluate to get the final result. So if again we have this number and we know this is in octal, we're gonna do the same thing. So as you may guess here, the number of bases, so we're gonna have for sure we're gonna have something like that, 8 to the 0, okay, times 1 plus 8 to the 1 plus 8 to the 2. Yeah, we don't have to write 1 because we know 1 times 1 is. So yes, this is, there will be, or you know, just for completion, we just write 1. Okay. All right, so in other ways, as you can see it here. All right, so the result is 73. We move on now to the hexadecimal system, and as the name indicates, it is base 16. For that reason, we're going to have 16 digits. You see them here on front of you, from the regular one from 0 to 9, these are 10, and then for 11 we have we indicate it by using the letter A, and then 11, B, and then C, D, E, F. F is indicating 15. So A, B, C, D, E, F now are really digits. So forget about them related to the alphabet. So they are digits in this case. The motivation for having this base is that any digit based on the 16 can be represented using 4 digits. So for example, 0, we can write it this way. This is 0. 12, 14 can be written as 1 1 1 0. 15 can be written as 1 1 1. So this is F, or 15. This is E, or 14, and this is 0. This is just sample. So why people chose this system? Because we can represent any of the digit using 4 bit, 4 binary numbers. Later on we're going to see more about bits, but let's understand them now. So this is the motivation, by the way. The octal, because it's can hold number from 0 to 7, then the reason why it was chosen, because we can represent any of these digits using just 3-bit, using 3-bit. So this is the motivation for having the octal and the decimal. So for example, 0 in octal written this way, and 7, which is the biggest number, biggest digit in the octal, is 111. There is no other benefit. It's just the early designer of computers thought these it was tedious to write things using binary. It was easier to write numbers using hexadecimal. For example, instead of writing this confusing number, so I'll just write its equivalent, which is just EF. So it's easy to read, easy for humans. All right, that is the motivation. Just let's look at how we do the conversion. And we're gonna quickly in this one, because I believe you already knew how to do the conversion. So here we have this number 2AE0B, and we'll be dealing with the base 16 in this time, but we're gonna do the same style. So let's see how we're gonna convert this. Okay, base 16 into base 10. All right, as we did exactly before. So we start by taking the first digit, okay, which is 11. So remember, we mentioned here, this is 10, this is 11, this is 12, 13, 14, 15. And the base 16, the power is 0, because this is where we start. And then next we go to the 0, and E is 14 here, and times 16 to the 2, A is 10, 16 to the 3, and finally 2 to the power 16 to the power 4. And just we calculate. Another example, if we were asked to get the equivalent of this number E5. So again, we're going to do the same thing. We're going to write the expansion. So here is the 5, and this is the position. So the first is in the ones, so it is to the 0, and E, because it's 14, so it's a 14 times the power 16 raised to the 1, and then we just calculate. So far, we learned how to convert from other system into the decimal, and we did that by multiplying by the base, and we add depending on the position of the digit. Now it is the time to understand how to convert from other system into the binaries. So we'll see how to convert from decimal into the binary, and as you may guess, you're going to be the opposite of that. So what we have done so far, when we converted from, say, binary to decimal, we multiplied by the base. This time we're going to do the opposite, which is we're going to divide. So in theory, and we don't want to get back down into this, when somebody said give us something like that, 16 divided by 4, okay, if we call this one N, and if we call this one B, then how we perform the operation, we say 16 using long division divided by 4, and we say, all right, the divisor would be 4. 4 times 4 is 16, and what is the remainder? 0 when we subtract. If we were given, if we were given, say, 17 divided by 4, then let's do the same thing, and then we're gonna have 17 divided by 4, and we use say 4, that is the divisor, 16. But this time we notice something different. When you subtract, we have a remainder of 1. Okay, so this one, what we see is called the remainder. So in general, we can write this. We can write it as this. So 16 is equal to the divisor, in this case is 4, times the quotient, which is 4, plus the remainder, which is 0. In the case of 17 divided by 4, we can write it as the equation as saying 17 equal 4 times this. I'm using the parentheses to indicate multiplication, times 4 plus 1. And this is the general format here. That's what we really mean by it. And the A sub 0 indicate the remainder. And notice that the remainder is always less than the quotient. Okay, that's all. But we're going to see how we're going to be using this idea to do the conversion from decimal to binary. Let's look. It's better to look at example. Okay, so it's not really necessary, but you can see here this is called the floor function. What is really mean if you give it something like this, 1/2, which is half, which is 0.5, it's gonna give you just 0. If you give it 1.6, it will give you just 1. In other words, you get rid of this portion. So for example, if I have 1.99, whatever number, okay, you will just ignore it. You're gonna only keep what comes after the decimal. That's all. So this is what is really what we mean by this one here. Okay, so let's say somebody give us the number 33 to the base 10, that is in decimal, and we try to find the equivalent binary. We'll find the binary. So what we do, we take that number, you see it here, it's n, we divide it by 2. So when we divide a number by 2, either the number have the 0 remainder or have 1. No, there is no other possibility. And we're gonna write the remainder here. When we see n mod 2, this is what we mean. We mean the remainder. So what is left after the division? So when we divided last time, when we divided 17 by 4, we said the remainder was 1. So we can say something like that now. 17 mod, this is called modular arithmetic, mod 2 is equal to 1. But 16 mod 2 is equal to 0. Okay, let's see how we're gonna get the equivalent of 33 in binary. So let's do it. So we take 33, we divide it by 2, we get 16, and remainder is 1. Okay, so this is the quotient, and this is the remainder. All right, and again now we're gonna take 16, we divide again by 2. Now 16 becomes our new n. We divide it by 2, we get 8, and the remainder 0. We carry this operation on, we keep doing it, right, until we get to the 1. When you get here, the result is 1, and here we have 0, then we stop. And then we see here, this will be our final result. So the number will be 1, 0, 0, 0, 0, 1. Okay, so we just found out how we find the value or the equivalent of 33 in binary. Let's look at another example, this time 18. So again, we're going to take 18 divided by 2, so 18, and now is 18, we get 9, and the remainder is 0. We take 19, so we take 9, we divide it by 2, we get 4, and this time we have remainder 1. We take 4, we divide by 2, we get 2, and remainder is 0. We take 2, divided by 2, we get 1, and the remainder is 0. We took 1, we divided, is 1, we divide by 2, and the result will be 0. Why is that? Because when we divide 1 by 2, let's say here I have 1 divided by 2, so we saw it's not enough, so what I need to do, I need to add the decimal here. Alright, and I have a 0 here, so then I have 5. Okay, 2 to the times 5 is 10, and we are concerned, remember this floor function, so when I give it 0.5, it will just give me the integral part, the one that before the decimal. Okay, and this is why we have 0 here, but we have remainder of 1. Okay, and you can carry on. Now it says 0 divided by 0 is 0, remainder is 0. I can keep doing this, it doesn't matter. So we finally we got our equivalent, which is here. And then how we're gonna write it, this is really important. This is the leftmost, so that means this one will be here 1, this is the 0, this is the 0 here, 1, and this one is the first. So this is really crucial, this is important how I write it down. So this is the most significant one, this is the leftmost, and this is the rightmost. Here is another method. So as you can see, we can do things in different ways. So in this course, we are not asked to memorize all of these methods. What is important is to know at least one. You may find some easier than others. It is your choice. No one will force you to choose any method. Whatever suits you, please use. Here is another way, which is equivalent. So let's say we have again 18, and then we're gonna write it as power of 2, the sum of power of 2. So 18, I can write it as 16 plus 2. Why? Because 16, if you recall, 16 is equal to the 4, and 2 is equal to the 1. So it is a power of 2. Okay, so we got 16 and 2. We form a table as before. We start by 1, and then multiply by 2, we get 2, multiply by 2, we get 4, and so on. And then we look for the location of 16 and 2, and we find them here and here. Okay, so what I got here, I got 1, 0, 0, 1, 0. This is really the equivalent. Here it is. Here is another method, and from my experience, students like this method. It's really faster. So somebody give us the number 21. As you can see, this is in decimal, and we are asked to get the equivalent in binary. So here are the steps how to do it. So what we do, we write the number on the right, like that. And then we divide by 2, and we write the remainder to the right of that, and we discard, right? We discard the remainder. We just write the integral part. What that means, if we get something 1.5, we just disregard the half. So 21 divided by 2 is just, we say, 10. Okay? And we're gonna, again, we divide 10 by 2, we get 5. So 5, you can consider it as being 4. You divide by 2, give you 2. And 2 by 2 is 1. And then we stop. When we get to the 1, we stop. That means we're done. Why? Because if we keep dividing by 2, then we're going to get 0, 0, 0, 0. And what we need to see, what we notice is that these are numbers. Some of them are even and some odd. Okay, so this is odd, even, odd, even, odd. So what we're going to do next is write beneath every one 1 if it is odd and 0 if it is even. So we write 1 beneath 21 because it's odd, and we're going to write 0 beneath 10 because it's even. We're going to write 1 beneath 5 because it's odd, and 0 beneath 2, and 1 beneath 1. And there we go, we got the equivalent. This is the equivalent of 21. Let's move to another topic, which is the conversion of fraction. So if we have this fraction, this is in binary, this is base 2, and you can see it's 0.11. And if you want to get the equivalent for that in decimal, we will do the following. But first, we do observe that if we're given a decimal value of 0.5, we can write it as a fraction, 5 over 10. These are the same. What we observe here, because this is base 10, we divide by the base. So we're going to do the same trick here. So we have 0.11, and then so we're going to just write them this way. We're going to just write as expansion as 1 over half plus 1 over quarter, or if you recall when we talk about the expansion, we said we have 2 to the 0, and then we have 2 to the negative 1, 2 to the negative 2, and we say these are this one is the same as 1 over 2, and this is the same as 1 over 2 over 2, which is 1 over 4. So we just did that. And then what we do, we add the values. Okay, so let's assume that we have 0.11101. So we're going to do the same thing here. So we're going to start, take the first digit, and start with the power negative 1, and we increase as we move to the right. We take the second digit and say times 2. This is mean multiplication, the asterisk, to the negative 2, and finally the final digit to the negative 3, and then we just add up. Another example, 0.011, all of these in binary, and do the same thing. All right, this is the first digit, and this one the second, and the third. We multiply by the base, and we keep decreasing by 1 until we have 2 to the negative 3, and then we finally just add. This one of course is 0. Let's say we want to convert from decimal to binary, a fraction. So we have this fraction, you see it here, and this one is in decimal. So we're gonna be following this algorithm, this step. All right, I'm gonna explain this step using this number. So what we will do, we're gonna write the number, you see it here, just copy it here, multiply by 2. When we multiply by 2, then we get they get a carry. What we mean by that? So for example, when I multiply 2 times 9 is 18, 8, and we have 1. We call this one the carry, right? This is the carry. That's something we carry over to the next position. So if I have something like that, 0.5, and I multiply it by 2, then I have 2 times 2 is 10, so 0, and I have a carry. The carry is 1. This is the carry. So this is what we mean by this. So when we multiply a number by 2, either we have a carry or we don't. It's as simple as that. So 2 times 0.3125, it gives us 625, right? Of course, 0 here, we just disregard the 0. So anything to the, we have a lot of infinity of them here, so we disregard them. So we end up with 0.625. So the carry is here, it's 0. And we get that number, right? And we repeat the process. We repeat the process. We multiply by 2. This time we have a carry, right here. So we record that, and we take the remainder. See what remainder is? What is after the decimal? Just a quarter, 2.5. We multiply it by 2, and we just get 50, and it makes sense. So that's 50, and the carry is 0, and 50 again times 2, we just get 1. It's half times 1 is just 1. All right. So we got our number. And what is important to notice that this is the most significant bit. It's the opposite of the integral thing. Unfortunately, there are numbers that keep repeating. So even in decimal. So for example, if we divide 1 divided by 3, right? If we divide 1 by 3, what do we get? We get 0.3333, keep repeating. The same story here with conversion from decimal to binary. Sometimes the process is not straightforward. Or the example we saw before, it was a nice one. Let's look at this one here. So we're gonna do the same process. We get the number, all right, multiply it by 2, and we record, all right, if there is a carry or not, and we repeating again and multiply by 2, and we get again, and so on. So we can see the carry here, as we did before. We keep repeating this, but we notice that in this case the numbers keep repeating and repeating, and at some point we just settle with some value. So we say, you know what, maybe we are interested in the first 5 of these. Right, then we're gonna keep only this guy, this guy, this guy, this guy, and this. Right, and ignore the rest because it's keep repeating. So sometimes we don't have to go all the way because it will be repeating forever. And the question, if somebody asked, the question normally will tell us to how many digits. All right, so we don't have to worry. And if you are curious to know why this one is repeating, you can look at the number and notice, for example, this and the number 0.5. 0.5, we can write it as a power of of 2. Okay, so we can write it as 1/4. But this one, no. That one is no. 0.23 is really what is 23 over 100. And if you look at the denominator here, it's 10 is really 5 times 2. 5 times 2. So if what happened with the 2 is composed of only 2. 4 equal to 2 times 2. Okay, so we call these prime, the prime component of any number. Here the prime component of 10 are 5 and 2. They are not all 2. And this is why the number is repeating. So every time, if you notice that the number, if you take it to its component, for example, if somebody give me 0. This is 15. Okay, 15. This is 100. This is just 15 divided by 100. So divided by 10. This is equal to, again, 2 times 5. You can see here also it is not purely consists of 2's. But you know what, maybe you don't have to worry too much about that. Just keep in mind that sometimes the operation can be repeating. Sometimes it terminates nicely with the example that was before. And in the case of 0.23, it keep repeating, but the question will tell us when to stop. One of the interesting thing about binaries is that we can do operations like addition, multiplication, division very easily, and the great mathematician Leibniz noticed that. So let's look at the how we do binary addition. All right. So it's because we have only 0 and 1, the possibilities are really limited. So when we add 0 to 0, the sum is 0. So this is the sum, and the carry 0 is nothing, right? 0 plus 1, again, the sum is 1, and no carry. But when we add also 1 plus 0, the same thing as before. In the case of adding 1 plus 1, right? So 1 plus 1 is 2. This is 2 in binary, by the way. This is 2. And we say, okay, the sum is 1, the sum is 0, and the carry here. So again, it's like saying 9 plus 1 in decimal. We say, okay, 9 plus 1 is 0 and 1. What is the 1? Is the carry. It's the same story here. Okay. So here we see if we can add more than 1. All right. So, but again, see 1 plus 0 plus 0 plus 1 plus 0 plus 0 is just 1. And here 1 plus 0 plus 1, we know this is 2, and we have a carry. Okay, and here 1 plus 1 plus 1, it is 2. So we have 0 and a carry 1, because this is just 2. And 1 plus 1, this is 3. And we have 1 and 1 carry, right? 1 and 1 carry here. Final operation here. So let's get more into it. So we have 1 plus 1, okay, plus 1. Let's do it in 2 steps. So we know 1 plus 1 is 2. What is 2? 0, 1. And then finally, when I add the final step, so 0 plus 1 is 1, and 1 plus 0 is 1. So we give out 1, 1, which is this number, which is really 3. Subtraction is a little bit tricky. So in order to do that, we will do something called to complement. But let's start by doing the most basic one. So we know that 0 minus 0 is 0, 1 minus 1 is 0, 1 minus 0 is 1. Okay, and if we have 2, we take away 1, we have 1 left. Okay, all right, so maybe this one will look a little bit confusing, but it shouldn't. Let's say we have this, let's say we are dealing with decimal. This is decimal. All right, so if somebody give us 9, all right, and we subtract. We say, okay, 9, we can't, we borrow this, so it's gonna 10 minus 1 is 1. So the same thing here, we borrow, so we have 1. All right, so we borrow from that, and when it says 0, we have 2, and 2 minus 1 is 1, like we did with this, and this one becomes 0. Like here, when we borrow this one, this becomes 0 as well. All right, so the same idea. Okay, so let's say we want to subtract the 2 numbers. You see them here. This is 7. We want to subtract it from 21. All right, so let's do it. All right, so we see here 1 minus 1 is 0. Then I come to this. I can't, so I need to borrow. So this one will be 2 minus, but this one will, I borrow the 1, you see it in red, and the result will be 1. Okay, and this one becomes 0. I need to borrow from the next one and from the next. Okay, and then I get this result, which is just 14. All right, you can verify this is really 14. But yes, very much the same way as we, in fact, exactly the same way we do, the same way we do subtraction in decimal. We just keep borrowing, and as we borrow, of course, we need to change the digit, like in this example, into 0. Binary multiplication is very easy. So when 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, 1 times 1 is 1. All right, and if this is for digit, if we have numbers like 1 times 1, which is really 3 times 3, we do the same way as we do with decimal. So we multiply the first, right? So we have 1, and then we move with 0, and we move and multiply, and then we add. All right, so 3 times 3 give us 9. Okay, and here's another example. All right, so because we have 3 digits, we have to repeat that 3 times. So, but very similar to the way that we do decimal multiplication. Moving on to a more interesting idea, which is how to handle subtraction. And the first thing that we notice that subtraction is really just addition in disguise. So what that means, if you ask me to subtract 5 from 10, then this is really the same as saying add 10 to -5. The same thing. Like somebody won $10 and then lost 5, what to get back is just what is left, 5. So we're going to use the same idea here. And this is really significant because what that means internally in computers, we need just to design some device, just do addition. And out of that, we can do subtraction, right? But in order to do this, we need to have a way to represent negative numbers. So in decimal, we just use this symbol to indicate this number is negative. How are we going to do this in binary? We'll see that we have some representation that help us do this. There are two systems, one system called the ones complement, and another one, the most commonly used, is called the two complement. Let's first look at the one complement. So what does really mean? You take a number, right, like this one here, and you flip them. If it is 0, make it 1. If it is 1, make it 0, and so on. So as a result, if this is the number, then this is its negative equivalent. Okay. All right, and you recall from the unit 1 when we discussed the inverter, it's like having, this is inverter. So we give it input 1, and make it 0, and so on. So it's a really easy, simple operation. This is the 2 complement. The 2 complement, the problem with it is not commonly used nowadays because what is a 0? A 0 can have 2 values, like this one. If we add these, if you add this number, what you will get 1, 1, 1, 1, 1. 1, 2, 3, 4, 5, 6, 7, 8. So we're gonna get 8 ones. Okay, I'm not sure they're 8, but anyway, if you add them, you will see 8. Another way to say, okay, this is a 0, is to have them all 0. So people didn't feel comfortable with this representation where we can represent 0 in 2 ways. So people came up with another system. Is called the 2 complement, which is commonly used in today's digital devices. But it is based on 1 complement. This is how it works. Let's say we have again our old friend, this number. So what we will do, we're going to get the first complement. So what that means, we just flip 1 to 0 and 0 to 1, and then we add 1 to the result. And we add. That's it. We get the negative. So if this is the positive number in green, this is equivalent negative. Okay, if we talk in terms of digital devices, then we have the number. This is the input. This is the input. So this is the number I want to convert to its equivalent negative. I pass it through inverter, and then I add 1. This is called adder. Just add 1 to this number. So like adding 1, 0, 0, 0, 0, and then this is what I get. So this is the output. So this is the negative. Now, since we introduce the negative numbers, we notice that we don't have special symbol. Like when we said we have 5, this is, we understood to be positive. The default is the addition. And when we are talking about negative, we indicate that using this sign. But now with the 2 complement, I don't have to do this. I don't need to have. This is the beauty of having the 2 complements. I don't need to use special symbol to indicate the sign of the number. Instead, what we have, we're going to use 1 bit here, the leftmost bit, okay, or the most significant bit. We're going to use it to represent, to indicate whether the number is positive or negative. So you just see here, so the number, you just take the first one from the left, and we designate that to be the sign bit, indicate if it is positive or negative, and the rest is called the magnitude, is on the right. Okay. So in this example, we see this is 0, so we know this number must be positive. Positive number. As a result of us deciding that the left most significant, so for example, if we have a number like this, so when we say this is the sign and this is the magnitude, you can see then the size, the inclusion of the sign bit. This is the sign bit. This is the sign bit. The inclusion of the sign bit within the number take place. So here are some equation. I'm not gonna go into detail into them, you can look at them, but here you give us the how big how many bits we can represent different number. So it may be interesting to look at them, all right, to see what they are. But in general, it depends. So if somebody want to represent unsigned number, what that means, you don't care about the sign, then how many bits? You just say 2 to that n, let's say 15 for example, all right, number 15. So I can say 2 to the 15 minus 1, okay. If I'm interested in the inclusion of the sign, then my range will be smaller, okay. Let's say I want to have n equal to 4, all right. Let's say for signs, for sign number, then I have the range from 2 to n, which is 4, minus 1 is 3, to 2 to the 3 minus 1, which is, well, and then the values will be between the range, the values between the range greater than or equal 8, negative 8, and less than or equal 7. Okay, so if you give me so what really this mean, if you give me some places to represent numbers, if you give me 4 places, then what I can accommodate into this, I can store from negative 8 up to 7. That's all I can accommodate here. And this is really important. This is really crucial later on when we will be talking about the registers. Later on, we'll be talking about registers. And also if you are doing some programming, let's say Java and other programming, will tell you how big memory location can store and how they decide based on this information here. And the reason for that, because we know that part of the number being represented is the sign. So here, this location will be where the sign bit will be stored. But if you don't care about the sign, then I can use them all. Okay, so you can see here, it's really, let's say I don't care about the sign, then it will be just 8. I'm going to represent 2 to the 4 minus 1, which is 16, minus 1 is 50. Okay, so what that means, I can represent from 0 to 15 if I don't care about the sign. Let's do some operations, subtraction in this case. So if we want to subtract 3 from 4, then as we mentioned, we need to get the equivalent of negative 3. So we know that 4 in decimal is 1, 0, 0, 0, and 3 in decimal is 0, 1, 1, or 0, 0, 1, 1. Now, we need to convert this one into using its 2 complement, and how we gonna do it? So remember, we take the number, we get the 1 complement, because 0, 0, 1, 1, and then we add 1 to get 1, 0, 1, so you can imagine that 1. So this is the negative 3. So you can see it here. Once we got that, then I'm gonna add these 2. All right, you see this is 4. This is 4, and this one is negative 3. I add, this means I add them up. So when you have to add 1 plus 1 is 1, 1 plus 0, 0, and so on. We're going to see the operation. But here it's really important to know this part is the sign bit. So this indicates that the number to the right is negative, and this indicates the number to the right is positive. So this is crucial when we get the results. So when we add, we get this number, and what we do, we just discard this value here, and then what we have, what is left is 0 0 0 1. Okay, and which is 1, right? Which makes sense, right? When we subtract 4 minus 3, the result is 1. Let's do another operation. Let's say 60 minus 24. We're gonna do the same thing here. This is 16. All right, how I know this is 16? This is the magnitude. All right, this is just 2 to the 4, 16. And here I know this is positive because the sign bit is 0. And this one is tell me that this is negative, right? And this representing 24. I add them up, I get the result. You can do it yourself to see that is really the case. Another example. Okay. So in this case, this is 10, this is negative 10. Okay, I add them up and I get, as we expect here, this value. All right, and here if we are to add two negatives, so negative 5 plus negative 9, all right, which we know is negative 14. So this is 5, and this is 2 complement, is that negative, and the same thing goes for the 9, and this is this 2 complement is negative. Then I'm gonna add these two numbers. Okay, and you can see here, in fact, I got negative number, so indicating the value. So if I want to know what this number is, what should I do? I'm gonna take it. I'm gonna take its 2 complement. Right, I'm gonna get its 2 complement. I'm gonna get the number back to know what it is, which is in this case just negative 14. Okay, this is a summary of the system that we discussed so far, the decimal and their equivalents. So I hope we now have a way, have more than way, in fact, to do the conversion between them. But what is really essential to know that, for example, the decimal has values ranging from 0 to f, which is, we say, it's 15. And as I mentioned in a previous slide, that the attraction, the usefulness of hexadecimal is that we can represent every 4 binary can be represented as one digit in decimal. That's why we like it. Even if you open Word and you look at the graphs, the values for the colors, sometimes they are expressed in hexadecimal. You will see X there, and you see number like this one, you see 2 3, you see 9, and so on. So each one of these can be, instead of writing 1 1 1 1 1, we just write F. So that is why we use hexadecimal. It's a good way to, a more concise way of talking about binary. So this is the best way to think about it. Okay, now we know how to get the negative for binary, given the fact that every hexadecimal can be represented using for binary. If somebody asks us to convert or to get the 2 complement of some hexadecimal number, then the process should be easy. We get that the number okay, in hexadecimal. We change it to binary, and now we know how to get the binary to complement. We do that, and we convert it back to hexadecimal. Let's look at the example. Let's say somebody give us 2a, all right? And binary, we know what 2a, 2 is 0, 0, 1, 0, and a is 1, 0, 1, 0. Okay, you see it here. So this is the equivalent. So we need to remember this representation, but with experience, it was easy. Okay, now I have just some bunch of binary numbers. I get there to complement. Here they are. All right. So what that means, I'm gonna the process. I'm gonna flip them and I'm gonna add 1 to them. So I get the sum value here. Now, how I'm gonna retrieve this one? You're gonna take the very first 4. Right, I'm going to get the first 4 here, and this one is 1001. This is just D, and this one 0110. This is 6. Okay, just so you can use the table that we have seen before. You can look at the table. Okay, this is the D, and this is the 6. Right. And from the table you can look up their values. Another method, another way. Again, you don't have to use this one, but this is another way. Some people find it easy. So what you do, you get the hexadecimal, you subtract from its maximum number, okay, and then you're gonna get the first first complement, and then you add 1 to get the 2 complement. Let's look at some example. Let's say again 2a. So 2a is 2 digit. What is the biggest number, right? So for example, if somebody give me 13 in decimal, what is the biggest number? 2 digit. The biggest number will be to have 9. Okay, because 9 is the biggest digit in decimal. So in this case, what is the biggest digit? FF. We subtract, we get D5, and we add 1, and we get the equivalent in the 2 complement. So 2a is the positive, and D6 is negative. A third method, when I think this is the easiest one. So what you do, you start by listing the number. You start, all right, we got just the number 0, 1, 2 up to F, and then do the opposite. You start from 0, 1 up to F. You see them here. Okay, here from 0 to the maximum, and then this is the opposite. Start from the biggest to the lowest. All right, and then you get the first complement, and add 1, and you get, then the final result will be the 2 complement. Let's look at the same example again, 2a. All right, so it's 2a. So go find it in the top place here. So we find this is the 2, I mark it, and then I find the a, I mark it, all right, and then when I look at what is under the 2, I write it here, and then I look what is under the a, I write it here. Okay, and then I just add 1 to that. All right, and this one give me the final result. I think this is the easiest one to do. I find it easier to follow, but anyway, I'm not gonna impose my opinion. So we have 3 methods. Whatever you think is easy for you, you go ahead and choose it. And finally, here's some example you may want to look at and practice your understanding of the finding the 2 complement in hexadecimal. Moving on to a new topic. This is called binary coded decimal, or BCD. And the idea behind that is as we notice, sometimes adding numbers or doing some operation on binary, if the number is small, is fine, but if the number is big, then conversion can be cumbersome. So people thought, you know what, let's just represent the decimal, right, from 0 to 9. Okay, so these are their representation, and we're gonna deal with them as if they were decimal. See what we mean by that. So one method is called 8421, which just stand for the power when it starts from 2 to the 0, 2 to the 1, and we get these. So we get 1, 2, 4, 8. So this is just a name. But at any rate, what really means, if I want to represent 35, I just take the equivalent of 3 and write next to it the 5. Okay, so you see it's 4 digits representing the 3 and 4 digits representing the 5. And if I have 98, so I'm gonna just write it 9 and next to it is 8. So this is easier instead of converting this one into binary, which can be a lengthy process. Sometimes maybe this is easier, at least as far as humans are concerned. But let's learn this method because it has some application. It can be interesting to use in some other application. But let's look at the example. If somebody give us this number and tell us this is not binary, this is BCD. So I hope this is really clear. This is not binary. This is binary coded decimal. We write a code for decimal. So how we figure out what is the decimal? What we do, we count 4 as we go from left to right. Sorry. So we have 1, 2, 3, 4, and this is another 4. So this one is 8. You can look at the table, and this one's 6. So 86. All right. Let's do the same thing here. So same thing. All right, so I'm gonna group them into group of 4. All right, we just need to be careful that we get really 4. All right, so in this case, what we have, this one represent 3, this one 0, 1, 0, this is 5, and this is 1. Okay, so we got 351. And the final example, C, again, we're gonna group them into 4. Okay. All right. Okay, so this one is 9. This one, 0, 1, 0, 0, this is just 4. This is 7. This is 0. Okay, so we got 9, 4, 7, 0. Okay, so I'm gonna leave this here as homework. I want you to try it, but you will see this. I'll give you a hint. You're gonna be a group of 3 groups. Okay, and this one you're gonna have 4 of them. So we're gonna write the representation in for the 0 and in binary, and the representation of 7 next to it, and then the representation of 1 in binary. The same thing here. Write the representation of 9, of 6, of 4, of 2. It should be straightforward process. Recall that BCD only binary coded decimal only recognize the digit from 0 to 9. So what that means for 0, this is 0, 0, up to the 9 is 1, 0, 0, 1. Okay. Anything else is not considered part of it. So in other words, there is no digit to represent 10. 10 is composed of 0 and 1. So to write 10, we have to write 10, we have to write 0, 0, 0, 0, and then 1 next to it to make it 10. So then because of this, we're going to have some complication. So what that means, sometimes when we add, as long as the result is within this range between 0 and 9, it's fine. But if we exceed, then we need to do something else. We need to correct the result. What we need to do, we need to add 6. 6 in binary is 0, 1, 1, 0. Let's look at some example. Let's say we want to add this number, which is 3 plus 4. This is 3, this is 4. Simple decimal binary addition give us this, which is fine. It's 7. 3 plus 4 is 7. We know just 7 is less than or equal to 9, then it's fine. But that's not always the case. Let's look at this example here. So we have 8. Okay. So when we add 8 plus 7, so 8 is 1, 0, 0, 0, and 7 is 0, 1, 1, 1. Let's go ahead and add. So if we add them, we're going to get 1, 1, 1, 1, which is 15. But that's not 15. We expected to have something like this. 0, 0, 0, 1. This is for the 1, and for the 5, 0, 1, 0, 1. Okay. We expect it to be this way. So this is not correct result. So what we do to correct it, we're going to add, we're going to skip the numbers that are illegal. Okay. So we're going to add 0, 1, 1. Let's add that. If when we add these, then we get this value. 1 plus 0 is 1. 1 plus 1 is 0. I have 1 carry here. I have 1, 0, 1. So what we get this number. So I need to make it into 8. So I have here 1, 2, 3, 4, 5. I'm going to have some numbers here. So what we're getting here, this one is 1, and this one is 5. See, I got the right number by how I corrected. I added 6 to it. Okay, let's do the same thing for this guy here. So what is 9? 9 is 0, 0, 1, 0, 0, 0, 1. This is 0, and 4 is 1, 0, 0. When we add, we're going to get 1, 0, 1, 1. And this one is 13. This is not acceptable. Again, we are expecting to get 9 plus 4. We expect to get 13. And 13, it should be something like this. 0, 0, 0. This is for the 1, and the 3, 0, 0, 1, 1. We expect something of this form. Okay, so let's see how we gonna go ahead and do that. Okay. So we're going to correct it by adding 6 to it. So what is 6? 1, 1, 0. And we add 1 plus 1. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 0. And we have here 1 carry, 0. And we have 1. 1. Okay. So let's see what we have here. So, and then we're just going to add, let's write it here neatly. So we have 1, 1, 0, 0, and then we have 1, and of course there is always 0 to the left, so 0, 0, 0. So again, we're going to group them together. Okay. So this one is this number is 1 and this one is 3 as expected. So in summary, we do addition, we add, okay, and then we see if the result is greater than, greater than 9, if it is greater than 9, then we need to correct it by adding, we add 6 to it. We add 6, which is the equivalent is in binary is 0, 1, 1, 0. And then we get the right result.